Lab 4, Circuits, by Advaith Nidumukala. The purpose of this lab is to predict the behavior of circuits in series and parallel and examine the behavior of ohmic resistors and capacitors using multimeters. Some fundamental principles are that the sum of voltage drops and gains in a loop is zero, and the current entering a node equals the current leaving the node in the circuit. Together, these are known as the loop and node rules, respectively. Additional formulas include that the capacitance of a capacitor equals the charge stored divided by the voltage across the capacitor, and the voltage drop across the resistor is equal to the current times the resistance. In this experiment, the system is the circuit and the surroundings are everything else, which may have some outside influence. Also, the PhET Colorado simulator was used for some circuits that we could not make in class. The initial conditions for our first circuit were an EMF of 3 volts, an R1 of 48 ohms, an R2 of 100 ohms, and the current is unknown. Using Ohm's law, the theoretical current in the circuit was 0.02041 amps, and the measured value was about 0.02 amps. The multimeter does not give more accurate or precise values beyond the second digit, and we also found that the orientation of the ammeter does not matter. When the circuit was disconnected and a voltmeter used, the potential voltage was determined to be 3 volts. The current becomes zero because the circuit is open and therefore there is no current flow. Simulated and real voltage drops at different points on the circuit are given on the right. Theoretically, the sum of the voltage differences at each point should be zero, but in this case it is minus 0.16 volts, which shows imperfections in measurement as well as outside influences on the circuit that are not accounted for in theoretical models. In the second circuit, the ammeter doesn't change because the resistance of the voltmeter is extremely high, and so very little of the current takes that path. The ammeter has lower resistance than the 100 ohm resistor, so in parallel, the circuit still shows a current of 0.06 amps. In the third circuit, a capacitor is added to a circuit connected to a light bulb. In this case, the light bulb initially shines and then the light slowly diminishes until it produces almost no light, and in this case, the capacitor is fully charged. When the capacitor is then flipped and connected to the circuit in the opposite direction, the bulb shines very brightly for a brief period of time as the capacitor discharges. The times are given on the right, and the slope can be used to calculate the predicted RC time, which in this case was predicted to be about 6 seconds, but in reality it was about 7. Some sources of error in our experiment include manual timing, so the stopwatch was probably not exactly timed at the instant that the occasion occurred. In addition, the wires in the battery are not ideal in real life. For example, in the simulated circuit, there is no internal resistance in the ammeter, but in real life, wires of course do have some resistance, which causes inconsistencies in the measurement. However, both the simulation and the real models are similar in that they both measure the currents through the circuit and they both use the same tools and equations to predict behavior. In general, however, the simulation is an idealized environment. To answer the first what if question, because there is internal resistance in an ammeter, there is some voltage drop in the real circuit. In the virtual lab, there is no voltage drop since the ammeter has zero resistance, theoretically. In the second what if question, the capacitor would charge much faster if the system was ideal, because the ideal model predicts instantaneous charge. However, it took around 1 second to charge the capacitor, which was timed manually by phone. And the internal resistance that the circuit elements have in real life causes this time delay. Thank you.